now before I share my screen and not after. And let's share my iPad right quick. All right, cool. About 2 more minutes and then we'll get started. So nobody has any questions about anything that we've done. So today we're going to start looking at some of these reactions of aromatics. And I've already kind of talked about the fact that we're only looking at electrophilic aromatic substitution where the ring is acting as a nucleophile. And so I want to focus on that. What's going on here? All right. So I want to focus on 3 of these reactions up front, and then the other 2, we're not going to go through the actual mechanism. You'll just need to remember. So the first reaction that we're going to look at, and I know it's in the video, we're just going to go through that mechanism, and then we'll kind of just keep working. So that first reaction, that halogenation reaction, we're going to look at that. And then we're going to look at the Friedel alkylation. And I'll give you a couple of examples of that and some examples where the product outcome is kind of different from what you expect due to some rearrangement. And also we're going to look at the Friedel acylation. So those 3 reactions we're going to focus on in detail with the mechanism for each one. And then the nitration and sulfonation, we're not going to do the mechanism for those. Let me see if I can cut this out and move it. Different page so we can walk through that mechanism real quick. Can put it right there. All right. So all these reactions, the halogenation, let me move that down and so I can put a heading up here. All right, so all these reactions have like very similar mechanisms. They all have like basically 3 steps. The first step is the preparation of your electrophile. They all want to go through the same process. Electrophile prep gonna be the first step in each one of these reactions. And then attack. So the ring attacks the electrophile, and then the final step, which is the crucial step, is reestablishing aromaticity. Right. One of the things about reacting aromatic compounds is that you never lose the aromaticity. It's always going to find a way to re-aromatize, because you lose a lot of energy by breaking up that aromaticity. I think it's something in the area of excuse me, 140 something kilojoules per mole of stability that you lose by breaking up the aromaticity. So they all go through the same basic mechanism. The electrophile is prepared, and that's what the purpose of the catalyst is. That's the purpose of the catalyst. The ring attached to the electrophile, and then you re-aromatize to get back to uh, the aromatic system, right? So you can see right here, and I'm gonna throw in something else in here too, because we already talked about directing effects. So I'm gonna throw another part, a piece into this reaction, right? So you can see we're gonna add bromine to the ring and using iron bromide as a catalyst, iron 3 bromide. And one of the things that to remember here is that, again, the aromatic ring is so inert that without the catalyst, there's no reaction that's going to happen. That's one thing. The second part to remember is only certain halogens you can only halogenate with certain halogens. I think fluorine and I'm sorry, bromine and chlorine work. Iodine doesn't work, and fluorine doesn't work. All right. So let's look at that first step, see what happens. We're gonna, and I'm just gonna rewrite it. So in that first step, here's bromine, and then it's gonna actually form a complex. Erase that. I'm gonna make that change the color of that. All right, so you form a iron bromide complex in that first step. That's how you prep the electrophile. And so what happens is, of course, even though these two are the same atom, you're going to create a little bit of a dipole this way, right? Because the iron is going to be pulling the electron density towards itself. So one of the bromines is going to become partially positive, the other one partially negative, even if it's only a small change in their polarity, right? So now that is actually ready to react with the ring. So that's the prep of the electrophile, and then you want to attack that electrophile with the ring. All right, so now the ring is, I'm just going to draw it here. And then this is plus. All right, so now this is going to attack here, boom, like that. And then break the bromine-bromine bond. And when you do that, you're going to get a rhenium ion intermediate, right, where the ring now has a positive charge on one of the carbons. Let's see, put it here. Right, and then that's going to be plus Br4, and now this whole thing has a negative charge, right? And so keep in mind that on the ring, on the carbons within the ring, right, there's still hydrogens on there. There's a hydrogen here, and move the plus charge. There's also a hydrogen here, right? And so the next step to re-aromatize or to reestablish aromaticity, let's see. Right, in order to do that, you have to do an elimination. Right, so I'm just going to show that. I'll redraw it down here. So iridium ion is here. And this is negative. And so the iron bromide ends up doing your elimination. Right, and that step is crucial. You have to reestablish that aromaticity. So now you're here. Plus HBr. And then remember, we talked about this also. The catalyst always gets regenerated. You never use it up. So that rearomatization step has got really two purposes. One is to reestablish the aromaticity, but then two is to regenerate catalysts. All right. Any questions about that mechanism? All right. So what happens if I take the product from that, and this is the other piece I'm throwing in just to kind of help us to kind of fold in another part of the lesson that we learned on Friday. What happens if I take that and I added bromine back to it? Again, what do you think is going to happen? I'm only asking this question because I want to see if you if you understand the directing effects. So what do you think? If I brominate the product, if I add another bromine to it, where's that other bromine going to end up?
At the other double bonds.
Okay, so when we think about, okay, so the ring is substituted. Is it substituted with a donor or an acceptor?
Bromine is an acceptor.
Actually, bromine is a donor, right?
Donor, right.
It's because it has those lone pairs around it. Right, so when you put a halogen on an aromatic ring, even though the halogens are electronegative and all the, they are great at causing induction and polarity, when you put them on an aromatic ring, they actually serve as a donor. So this is a donor. And what kind of directing effects would a donor facilitate? Is it going to be ortho para, or is it going to be a meta director? Remember, this is ortho, this is meta, and then this is para. Let's go back up to what we talked about.
Ortho para.
It's an ortho para director. We can go back to what we talked about on Friday. Actually right here, right? So with a donor on the ring, it's the ortho site, which is right here, and the parasite, which is right here, that get activated. So anytime I have a donor on the ring, when I add a electrophile to that ring, that electrophile is going to go either to the ortho or parasite. So when you have a donor, you get two products. Right, you're going to get out the ortho product, which would be page break right there, which would be here. It's the ortho product, and then you'll also get the para product. Like that. So this is ortho, and then this is para. All right. The question now, here's another question. Of those two products, which one do you think is going to be favored? Because you're going to get a mixture. It'll be present in a specific ratio or a particular ratio. But which one do you think is favored? And why?
Would it be the one on the left?
The ortho?
Yes,
Why do you say that?
because it reminds me of when we were doing the denophiles and stuff like that.
Mm-hmm.
So it's like in the cis transformation.
Okay. I understand the answer, but in reality, it's the para that's favored. Right? The para is favored. And there's a reason for that, right? I'm gonna write that down here. Right, the reason is because of sterics. Like we've been talking about sterics a lot. So the two bromines are further away from each other, and that's good. Sterically, that's good, and it's also a little bit lower in energy. But here in the para product, you see the bromines are closer together, so it's a little bit more steric hindrance. So we call that sterically hindered. Right. So the para product is usually your more stable, it's usually favored, just because of the fact that you have your groups further apart from one another. All right, any questions about that, about the reaction? Any questions about the directing effects? All right, let's do another reaction. We're gonna do the alkylation this time. Let me just cut it or look at it and see what it is. That's all right. I can do. I'll just make one up. So for your and this is the proper name for it. It's called a Friedel Crafts alkylation. All right. And so that's taking a aromatic ring and an alkyl group, normally an alkyl halide. And you react this in the presence of aluminum, right? Aluminum trichloride. And what you get from that is the aromatic ring with an alkyl group attached to it. All right. So you normally start with the alkyl halide for that. And again, you need a catalyst. You need that aluminum catalyst to facilitate the reaction. And at the end of the reaction, you're always going to get that catalyst back, right? So let's take a look at how this works. You know, the first step is the preparation of the electrophile. So in this case, you have methyl iodide, and again, it's going to complex with aluminum, right? And when it complexes, you create again polarity here, so that's going to become partially. It's already partially positive. It's going to be more positive, right? And then in some cases, the halogen will actually get pulled off. In this case, it won't, because that carbocation that you would make from that methyl group, it will be too unstable. But if you have a more substituted alkyl halide, then you know that you can generate a carbocation intermediate, right? But for now, this is fine. And then when you get to the next step, the ring is just going to attack. I must be writing too big today. Keep running out of space. So the ring just is going to attack that electrophile. So here in the next step, you have your aromatic ring here. Right? And then this attacks here like so, just like in the other reaction. Right? There's not a whole lot of difference in the mechanism, more so than there is a difference in what's reacting, right? The mechanism is pretty standard for all three of these reactions: the alkylation, the acylation, as well as the halogenation. All right. So when that happens, what I get from that is this intermediate. We call it the rhenium ion. It's common to all of your electrophilic aromatic substitution reactions. Right. So that's my rhenium, and then CH3 is here. Sorry about that. And remember, there's a hydrogen here, and that'll be plus AlCl3. Just gonna put the iodine out here, and that's negative, right? So you end up, again, once the ring attacks, you generate a anion and a rhenium cation, and then that anion is your base for the next step, right? So for rearomatization. Right, so you just take that rhenium ion, and I would just draw it out up top, but I want to make sure you understand what's going on. That plus that, and then of course this is going to do your elimination, right? And then once you eliminate, you're back at your product, which is the alkyl version of or the alkylated aromatic ring plus, let me say HI plus AlCl3, aluminum trichloride. Right? Any questions about that? All these mechanisms have the same 3 steps. You prepare the electrophile, the ring attached to the electrophile, and then you re-aromatize. Which step do you think is rate determining? It's the slow step.
The attack.
Yes, the ring attack of the ring is going to be your slow step. Simply because when you break the aromaticity up, that takes a lot of energy, and so that's not going to happen readily, right? So that's going to be your slow step compared to the re-aromatization and then the complexation with the catalyst. All right. So again, let's see if we can take this a little further. What happens if I take, I'm just gonna put it here. So what happens if I take the product that I made up top and I brominate it? What do you think? I'm not asking for the mechanism. I'm asking you to predict what happens, predict the products. Right? What type of reaction am I doing based on the reagents?
Is it a halogen reaction? The one we did earlier?
Yeah, it is. It's a halogenation. That's exactly right. And so what does that reaction do to aromatic rings? You're absolutely right. 1,000%.
So that means it's gonna break another double bond.
It will. But let's not think about the mechanism per se. I want you to think about the outcome. What does this set of reagents do when you expose a aromatic ring to bromine in the presence of iron bromide? What's going to happen?
Is that bromine gonna be added to the 4th carbon?
Yes, it's going to add to the ring, right? And now here's the other question. If I know it's adding to the ring, where is it going to add to the ring? And that's going to be determined by what's here, right? So is the methyl group a donor or an acceptor?
Acceptor?
Donor.
It's a donor, right? All alkyl substituents on aromatic rings are donors through induction. Remember I said you can donate or accept through induction or resonance, right? So carbon is really electron rich. So it being attached to a ring is going to donate electron density to the ring through induction. Let me fix that bond too. That doesn't look too cool. All right. So it's a donor. So that means what? What kind of director is it?
Hello.
It's an orthopara director, right? Is that right?
Yes.
Mm-hmm. So where's bromine going to end up in the products? This is ortho right here. This is meta, and that's para. So you're going to get 2 products One of them is going to be the ortho product. Uh-oh, sorry about that. So it's here. And the other one is going to be the para product. Like that, right? And we can, again, we're applying the same logic. Which one is going to be favored? What do you think?
Pair.
Para, right? It's less sterically hindered than the ortho product. More than likely, the para product is going to be present in a higher amount. Is that making sense?
Yeah.
All right.
Yeah, it does now.
I just want to make sure we all on the same page. All right. We actually got one more reaction that we're going to look at. And it's the acylation, or Friedel Crafts acylation. So I'm just going to write it. I don't have to cut and paste because I remember what it was from up top. All right. So we're going to So Friedel Crafts acylation. So an Acl group, let me just go ahead and give you what that means, right? So when we say we're acylating something, what we're doing is adding a carbonyl. That's what we call an Acl group, right? So this part of the carbonyl, this carbon, is what's going to be attacked. All right. Anybody remember when we made aspirin? There's a lot of different ways to acylate, but anybody remember when we made aspirin? That was a type of acylation. All right. Because I'll just write it down right here real quick. Right. We took salicylic acid, which is here. And then we added acetic anhydride to it. Right. And what we got out from that is acetyl salicylic acid. So this part right here that we added, that acylated that oxygen. Right. So aspirin synthesis is a type of acylation. Even though the end product is an ester, so it's also considered an esterification, it's still a type of acylation reaction because we added a carbonyl in. So let's go ahead and look at the Friedel Crafts acylation. Erase that. All right. So we're going to take our aromatic ring here. Let me switch the bonds around. And we're going to react it with an acid chloride. Right. That's a key functional group. I'm just going to put a CH3 out here. Right. This functional group is called an acid chloride. Right. So it's like a carboxylic acid, but instead of an OH, you have a chlorine out here. All right. Those are the acid chlorides are really highly reactive and they're great acylating agents. All right. So I'm going to take that. And again, I'm going to use the same catalyst I used before, which was aluminum trichloride. Right. And so the outcome of that reaction is an acylated. Oh, that ring looks terrible. Sorry. So that's the outcome, right? where I've added the carbonyl group to the ring. So now we need to look at how that happens. So the way that happens is the same as the other reactions. It's electrophile preparation, followed by attack of the ring, followed by rearomatization. Right. So your electrophile in this case is the acid chloride. And in this case, you actually do pull off the halogen. So let me put a dividing line here. So for my electrophile prep, I'm going to, let me zoom in so I don't write on that line. I'm gonna write it like this. Right, that's gonna coordinate with aluminum trichloride. You actually break this bond, right? So you end up with this. Right, and of course that's negative. So this is your electrophile. This is what the ring is actually gonna attack. Right, and so now in the next step, which is, I'm trying not to write on this little page divider so it doesn't get cut off when I post it. So it's here plus this. Right, and so that's the acylation step, right? So this is the attack step. And you end up with your ring. Keep the plus bars up top like we had in the other examples. And then now this is here. Yeah. Like so, right? And then the final step is the same. You rearomatize. You're gonna take the hydrogen that's right here and remove it. Do an elimination.
Oh.
All right. All right, so aluminum tetrachloride is negative. And pull that proton off. Boom, same exact arrow, same exact everything, right? Right, and then you regenerate your catalyst and reestablish aromaticity at the same time. Not what I was trying to do. We'll work with it though. All that up. It's Monday. All right. Any questions about that? About the mechanism for the acylation, for the halogenation, for any of the reactions we've done? All right. So again, let's ask this question. What happens if I take the acyl or the acylated ring and I add, let's say, let me go back and add, and I wanted to alkylate it. Where's that CH3 group going to end up? Because this is what I'm adding to the ring.
Is it ortho and para again?
Mm-mm. Or what types of groups or substituents cause orthopara direction or force orthopara direction?
Donors.
Donors.
Oh,
And
is this a donor? The carbonyl group?
No carbonyl acceptors.
Yeah. Think about it. The carbonyl carbon is partially positive, right? And there's a big dipole between the carbonyl carbon and the oxygen. So this is an acceptor. So if it's an acceptor, instead of it being an orthopara director, what is it?
Meta.
It's a meta director. That means whatever you add is going to add here. This is meta right here. That's ortho, meta, and para. So if I add that CH3 group in, it's going to add right here. Right. So anytime you have an acceptor attached to the ring, it's going to cause your electrophile to come in to the meta position. And anytime you have a donor on the ring, it's going to cause your electrophile to come in at either ortho or para. All right. Any questions about that? Yeah. Again, if you look at the notes from Friday, we talked about like why that's the case. Let me go back to it. So we talked about how if you put a donor on the ring through resonance, it's going to activate ortho and para, right? Because you can see in the ortho example in the middle, you got a pair of electrons at that ortho site. And then if you draw the next resonance form, you'll have a pair of electrons at the para site, right? So that's how donors activate the ring. And then we talked about the ring being deactivated by acceptors like carbonyls, right? Because they pull electrons out of the ring either through resonance or induction. But you can see at the ortho site for an acceptor, right? There was where is it? Oh, up here. There's a positive charge at the ortho site right here. And then if we draw the next resonance form, there's a positive charge at the parasite. And so I can't add an electrophile where there's a plus charge. All right. Any questions about anything? All right. There's one other example I want to show you, and then we're going to stop. And then Wednesday, I think Wednesday we can work through some some other problems. I'll find some problems in a different book to work through. It won't be that many for Wednesday. And then Friday we have an exam, and I'm probably going to use that responders instead of using Proctor U, because I think we had a problem with them. I think they got hacked too recently. So I'm probably gonna use that responders lockdown browser for the exam Friday. Let's see. All right. So let's look at one other problem here. And we're going to end with this. So I'm going to do take that off. I can get my So I'm gonna use this alkyl halide, and the product that I end up with from this alkylation is actually this. The expected product would have been this, but we don't see that. All right. So what do you think happened? Let's go through the the mechanism. All right. So the first step, because we can explain it, you can actually explain it after the first step. Right. So the electrophile prep step. Let's look at that. That's going to be your alkyl halide plus aluminum trichloride, right? So you're gonna, let me not put a plus here. That's gonna form a complex, right? And then once that, again, with the methyl example we did earlier, that probably would not result in a removal of the chlorine. But in most cases, once you form that complex, you actually generate a carbocation, right? So here, you actually get this carbocation plus AlCl4, and that's negative. All right. What type of carbocation is that? Is it primary? Is it secondary? Is it tertiary?
Primary.
It's primary. Is that good or bad? Right. That's a really unstable carbocation. Right. And if we look at the product, it looks like the carbon here is the carbon that got attacked. So how would I put a carbocation at that carbon? What could I do? We've done this before. It's not new. And I'm going to write this out so you can see it. What can I do?
hydrogen shift.
I can do a hydride shift, right? So this is going to rearrange. I'm not writing on the line. I think I am. Let me just move this down. So I do not want it to get cut off. It's going to rearrange. Why do hydride shifts even happen? Why do these rearrangements like that even happen?
To make stable carbocation.
Yeah, it's all about stability, right? You go from a less stable carbocation to a more stable carbocation. So this is CH2, and that's going to be positive. I'm going to take the hydride from the carbon next door. I'm just going to move it, the hydrogen and its electrons, right? That's why I put the arrow on the bond to show that it's actually the whole thing is migrating, right? The hydrogen and the electrons from the bond. So you end up with this cation. I think I have the extra carbon. I'm missing a carbon in the product. I'm gonna fix that though. So I end up with this cation right here. This becomes a CH3, and now that's positive, right? And this is what the ring is going to attack. Right. So those alkylations, sometimes you'll see those I need another carbon right here. And I need another one over here. Never fear, I can fix it. Right. So a lot of times when you do these alkylations, you see rearrangement depending on the type of alkyl groups you start with. Right. So in this case, this thing rearranged to give you a tertiary carbocation, which is more stable than the primary carbocation that was made during that electrophile preparation step, right? So I just wanted to point that out because on Wednesday we'll work a couple of examples where you may have a carbocation that's shifted, and you got to show that in the mechanism. So we're gonna stop here. Let me stop the share and